And then we'll talk about ion channels specifically. It's a fairly short lecture. That could be a really long lecture. That could be a whole course. But I'm going to point out some cool stuff about ion channels. So I thought we'd first just simply go over some of the key elements of the Ax potential. Right? So we could start with two basic things. One is that it is obviously conducted along the membrane. But the first question is, where does it start? Remember the name of that spot? You can get out, you can open up the last lecture. You can ask your friend. Remember where is that Ax potential, or often called a spike, where is it initiated? That's that axon hillock. Right? I'm writing this out so I can see how to use a document camera, because we're going to really talk in detail about the Ax potential today. But if you record from a cell, you poke an electrode in it, and you inject some current, okay? Where's the point where you get an Ax potential? What do we call that? So you're injecting current that causes a voltage change in the membrane. So voltage is going to go from more polarized or polarized, right, to less polarized. We say it's depolarized. So where's that point where you start, where you fire off the Ax potential, or what that's called? So it's that little teeny bit above the threshold. Now, this is a little bit more difficult. Do you remember what we call the threshold in terms of physiological parameters? How do we define that? So, go back through the basics. Always start step by step. You've injected current, okay? Somehow. You've made a voltage change. The voltage in the membrane of the whole of that neuron, where you're controlling it, call that a space clamp. You're controlling all the voltages all over that place, okay, including that axon hillock, that spike initiation zone, right? And so you start to depolarize. What happens to the channels? They start responding, right? They're voltage sensitive or voltage gated, okay? When the channels open, ions flow. When ions flow across a membrane, in this case an insulator, what do we say that is? When we separate charge, that's voltage. When ions or charge flow, that's current. Actually, you could just throw out guesses. Voltage, current, resistance. Okay, so current, and we give that the term I, all right? And usually for a particular ion. So the current for sodium. So those sodium channels, didn't you see this well enough in the back? Pretty bad handwriting. So we start getting some current through the sodium channels, right? Because they respond. Well, we need a little bit of a voltage change. And actually, they respond really well to the rate of voltage change. Right? So if it's really fast but small, they'll go like this. They'll all start responding. So they open, ions flow, ions flowing, that's current. That's the definition of current, right? So the threshold, we say, now we'll talk about the threshold, not just a little above the threshold, right? Is where the sodium current is equal to, do you remember? Potassium current. Why do we talk about the potassium current? Well, remember there's a resting potassium current, right? But they're also responding as well. Remember they respond more slowly. So the threshold, that is right at the door, not through the door yet, right at the door, that we say is when they're equal, okay? So again, you have to think, as you're stimulating, the system's responding, okay? Now, one thing that we didn't really cover, we'll go through this a couple more times here today and even in the review, but when sodium gets the upper hand, okay? So now the spike, or AP, okay? That's happening when we say when the sodium current is just a little more than the potassium current. So now a little sodium gets the upper hand. A little bit more comes in, right? Starting to make the inside more positive than it used to be. Remember, the inside's negative. So you're making it, relatively speaking, you're making it less negative, less negative, less negative. Remember, it goes to the overshoot, goes to 0, goes to the overshoot. But at that early stage, okay, just past the threshold, sodium has got the upper hand. What's that going to do? Current is flowing. It's biased toward sodium going in, making it more positive, right? So that's moving the voltage this way. So as sodium is going in, it's pushing the voltage in that direction, right? So this is why we say it's regenerative. You've probably seen that term. Or it's like, you know, the fuse, the gunpowder, whatever. As the sodium comes in, that's depolarizing, so it depolarizes a little more. It opens more sodium channels, which depolarize a little more, and so it's like a runaway train, whatever analogy you like, okay? Spark with gunpowder, you know, the heat, the gravity, whatever, that's using the system. But in this case, we're talking about sodium is generating a change in voltage, and it can only go toward what? The equilibrium potential for sodium, okay? Remember, that's that driving force. So because there's a strong driving force, sodium starts to open, it starts to cause a voltage change, and that is regenerative. That's why it takes off like a rocket, okay? So it's a little more to say that, well, sodium is accounting for the rise of the Axe potential. It's accounting for many aspects of it because more voltage change, more sodium channels to respond, right? Okay, let's get back to this axon hillock, the spike initiation zone. So again, you record from a cell and you're recording all the voltage change all around the whole cell. When you see that spike, so remember we saw a little picture of a cartoon of a neuron, electrode in it, gave it an injection current, and you got an Axe potential, right? Well, where's that really happening? It's actually really happening at the axon hillock. But that voltage, you're measuring over the whole cell. So it doesn't matter if there's a little voltage change over here. Actually, it's a really concentrated bit of sodium and potassium channels at that axon hillock, okay? So even though you're recording a little farther away, you're recording an average voltage. Okay, so in the end, you're really seeing, when you record from the cell, you're seeing the start of the Axe potential at that axon hillock. And then it goes from there, obviously, down to the synapse. So what do we say? Formally, under normal conditions, is the parameter there, okay? Or the characteristic of the Axe potential. Starting, so it's unidirectional, or you could say, we'll just say directional, but it's starting at that axon hillock, and it's going to go that way. It's not going to go a little ways and back up and go sideways. It goes right down there. And again, it's regenerative. And how is it regenerative? Okay, so sodium is coming in. I said it's inching that voltage up, but where is it doing that? Here's the Axe potential. It's moving along. What do we talk about in terms of current flow as it comes into the axon? Where does it go? It spreads forward, remember? Remember, even in a physiological system, when you have current flowing, it flows in circuits. You can't just have charge go over here and end up over there. It doesn't do that. So it's going to flow down the axon. So that regenerative effect is that flow of sodium in front of it, right? But then we also talked about propagation. Well, what I just described is propagation, right? It's going to propagate because in front of the Axe potential, it's depolarizing. It's starting to bring that voltage up to threshold. It does that over and over again. It does it very smoothly, right? Normally, in a cell that's not myelated, and a cell that is myelated, it jumps, but we're not going to worry about that. So it's going in one direction. What else can we say about the Axe potential? So this is a basic property, if you will, this directionality. Well, what's the other thing that we often, one of the first things we say about the Axe potential in terms of how it looks as you go down the axon?
Uniform.
It's uniform, right? All or none, we say. that's going to depend on the axon. One axon will look one way, look that way, all the way down the axon. Now when Hodgkin and Huxley recorded from that little piece of squid giant axon, were they able to tell that? No, because remember what they did? They shoved that electrode all the way into the inside of that segment of axon, and they basically recorded an action potential all at once over the whole segment, right? So now you have to come along and be able to measure it at the beginning, you know, quarter of the way down, halfway down, and so forth. So that came later. It was very, very clear when you could measure very carefully along the axon what the size of the action potential is. Okay, and you can see that it basically was the same all the way down to the nerve ending, and the nerve ending has a huge wave of depolarization, opens up calcium channels, the synapse, and fires out some neurotransmitter. So uniform in size. What else? Well, we talked about the orchestration of the ion channels. Okay, so we're going to talk about that. What about, so we talked about, or I'll go ahead and put this on here, propagation. This is tied to directionality, all right? So there are a lot of elements that go into propagation. We've talked about them already, but there is one thing in terms of the directionality of the propagation as well. And that is behind the action potential, what do you have?
The deactivation of the sodium channel.
So you have the inactivation of the sodium channels, and that produces some property we call that membrane is unable to fire. We say that it is refractory. But there's two elements to the reason why that membrane right behind the action potential is refractory, right? So one of them is that the sodium channels have inactivated. So you have this separate gate, and it will come to some appreciation of that today later in the ion channel lecture. But so that separate gate, it closes so that they're shut. Okay. Now this is what we call a voltage state dependent effect. So it's really, really strong at the top of the action potential. But remember, the action potential is really fast, right? It lasts a millisecond or two. So what's happening during the falling phase of the action potential? Sodium channels are inactivated. Who's bringing it down? Potassium channels. But their, what we say, conductance or their effect is really, really strong, right? So then the voltage goes down to where? It goes down to this really low point, this undershoot, right? And that undershoot, okay, the sodium channels are just out of the picture. They've been chopped. So now you have potassium channels, but they're really, really strong. Lots of them are open, very high conductance, okay? And the undershoot has gone below the resting potential. So where did it go? Where can it only go? If it's hugely dominated by potassium, potassium is dictating the voltage, that is the polarization. Where does it go? What do we call that? That's the equilibrium potential for potassium. So that's the second part of the refractory period. That membrane has just been clamped down there by potassium. And, you know, as hard as you push, the early phase, as hard as you push, you can come in and, you know, we have an electrode there, and you just put in a huge amount of current to try to depolarize it. And it won't respond, won't respond, won't respond. Sodium channels are inactive, and it's just clamped down there by potassium. So those two parts are essential for really holding that membrane behind the action potential in this refractory state, meaning you can't get an action potential. And why do we want that? So it won't propagate backwards. So at the axon hillock, it won't just go like that, right? Okay. Or can it? All right. Normally, as it starts going down the axon, it won't just start to go backwards. It won't just sort of splinter off, right? So that's a big part of unidirectionality. But what about signaling? It keeps them separate. But then this sounds like an exam question, doesn't it? It puts an upper limit on the frequency that you can generate in an axon, right? Remember we talked about them, I'm not sure we did. We talked about the rate, we didn't talk about the frequency, did we? So the upper end of frequency is about 100 per second. We call that 100 hertz, okay? Can't get much more of that out of even a big myelinated axon. So they'll run as close as they can together, all right, but they stay separate even at high frequency. Key thing. Any questions? So yeah, this is all in that key list in the presentation, the PDF of the PowerPoint. But I thought we'd go back through these and make sure that you have a chance to think about these, but also if there are any questions. Now you may have questions and you're keeping them to yourself. That's okay. They can come out later. So what I'd like to do now is go through the axe potential step by step, all right? And I'm going to use the dock hammer for this, all right? Because I'm a little old school. Actually, I've used the board, but I think that's even too old school for everybody. So fundamentally, I think you can all draw an action potential. So the way we normally measure it is a voltage change, right? And we give that a V sub M. All right, that's just a convention. All right. And I'm going to make this 0. And the units are going to be millivolts. And this is minus down here, and we're going to say, we're going to have 2 positions down here. I think some of you already know why. This is going to be, and I'm not going to do this perfect scale, but this is, say, going to be minus 65. And, okay, it's already bad. Up here is going to be plus 55. Can you see that? All right. So I think you can all draw an axe potential. You've seen it over and over again. You know, it goes like this. You can even do it in the air, right? So question is, what's going on at each stage? All right. And how, what we're going to do underneath here is we're going to relate it to the current. Okay. So first off, the resting membrane potential is here in the axon, or often in most cells. Okay. But where's that equilibrium potential for potassium? There's another notch there, isn't there? It's just below the resting potential, right? So I'm going to put a big E. Remember, we used the convention E for the equilibrium potential, but it's a potential, so even an electrochemical cell, we measure that as a voltage. So we can stick it on this axis, right? So it's E sub K for potassium. There's a reason why it isn't P. Okay. He's from the German. So at any rate, we know that the rest potential is what we say a little above the equilibrium potential for potassium, okay? Or it is, the membrane is slightly depolarized compared to the equilibrium potential for potassium. Why? Well, we know that it is, even if you just look at the axe potential, right? Because the undershoot is lower than the resting membrane potential. We said, okay, that's where the equilibrium potential is. Hopefully I'll draw it correctly. Okay. Put that undershoot right where the equilibrium potential for potassium is. But why is it a little bit depolarized? Let's say you didn't know. How can you depolarize the membrane? Okay. Membrane over here, it's relative to the outside, it's negative, right? So this is the outside. This is the inside. So you want to depolarize it. There's this leak channel, but just say in very general terms. So the answer, yes, is the leak channel. Positive, okay, so what's that doing? So there's this little leak channel. So a little bit of positives coming in. So you're negating that negative, okay? The other way would be to take away some of the negative, but we don't do that. So a little bit of it turns out it's not all that perfectly selective, this leak pathway, but it's mainly sodium coming in. Sodium is positively charged. So start with this. Just remember that you have a polarized, you can all see that in the back, right? Polarized membrane. You're adding a little bit, very, very slowly. Leak, you know, leak sounds slow, right? And it is. So it's even slower than the resting potassium conductance, all right? It's just dribbling. They could have called it the dribble current. Okay, so it's dribbling in, but it's just enough, and it's constant. So it is bringing positive in. It's offsetting the potassium going out. So positive's going out. That's making inside negative, relatively speaking. But an electrochemical cell, we can define it that way from the Nernst equation. And so a little positive's going the other way. It's coming in. Positive going in is depolarizing. Positive going out is what we call hyperpolarizing, all relative, okay, or polarizing. Okay. So that's where it is. It's a little below that. Okay. Now, right here, we give the current. I'm just going to write inject. We're not really injecting. I mean, in essence, you're putting in some charges, so perhaps you are, but what happens? So we're injecting positive current. So it's going to go in the direction like the leak or even the sodium channels, right? It's going to depolarize. So it starts to depolarize. And remember, it takes a little time to do that. What happened there? Why did it take some time? What do we know? Go back to basics. What do we know about the membrane? It's an insulator and a capacitor. So as you charge it, you have to coat charges on the membrane. You have to charge that capacitor. Therefore, this is due to the capacitance charging. Just flipping that point around. Okay. So again, why am I pointing this out? That again can really vary from one nerve cell to another. In some cells, really small, and there's really high density of channels, okay, then it can charge very quickly, to the point where it really is negligible. In some cells, very large cells, lots of membrane may even be enfolded, okay, not so many ion channels, it can take a long time. It's really the amount of charges moving over time, and then the capacitance of the membrane. So why they say when it's bigger, it takes longer? Well, bigger membrane, more charge to add, okay? So that's going to just basically intuitive. So then we get to this point here. I'm going to put it just slightly underneath that, okay? What is that? What am I drawing? Well, you don't know yet, do you? Now you do. Right? What was that? Oops, I went too far. All right, I make a big blob here. So now you know what happened, right? So that dotted line's just below where that voltage hit, right? This is real quick. So what's the dotted line? That's the threshold, right? Because it took off right after that, didn't it? Went up here, it's supposed to stop right there. And then it comes back down. All right. Give me a break if this isn't perfect. But now it's coming back down to here. And it stays there for a while, stays there for a while, stays there for a while, and comes back up. Okay. These are supposed to line up, and EK is supposed to line up with that. Not horrible, but it's not perfect. Okay. So, what happened above threshold? What's driving that spike up to the top? In this case, it's highly idealized, okay? So it's going all the way up and it's stopping. So sodium dominating the system. We'll forget about the other guys. So sodium is really driving that up. So, and it's okay to just put sodium here. But then what happened here so that it stopped? Inactivation of the sodium channels, but not just that. So if this went up to this position here, and I'm going to say, this is idealized for purposes of instruction. This is actually, I'm saying, the equilibrium potential for sodium. Does that make sense? Potassium and sodium are both positively charged. How can they have completely different equilibrium potentials? Well, they have completely different directions of their gradient, right? Potassium's facing outward, sodium's facing inward. So even though they're the same positive univalent cation, right? When they go in different directions, different effect on voltage, right? So sodium coming in, that's doing this here again, making more positive, more positive, more positive. So now if this were the sodium channel, okay, that's the leak one. Now we'll make the sodium, put the sodium channel over here. Okay. So now you have a lot of charge in here, and it actually flips. So up here, you've now flipped the voltage arrangement. It's good to have. So these things are nice tools to have in your mind. Okay, you know, positive inside, and you add a little bit that can help you get to the path of figuring things out. Now, this is highly idealized. The active potential rarely ever gets up to the equilibrium potential for sodium. But if it did, okay, and let's say we forget this part of it, it just went up. Okay. We're now going to talk about a component that we didn't talk about from the key list. But so it went up to there. It hits the equilibrium potential for sodium. And then we just stopped right there and we looked at what was going on. And let's say this happened just, you know, some microseconds before the channel inactivation happened. So the channels are open, aren't they? Because those channels, it turns out, really, really respond to where the voltage is. So down here, the sodium channels, they're all, the ones that respond during the active potential here, they're all closed. Okay? But they're not inactivated. They're closed and activatable, we say. All right? Okay. This is just supposed to mean not just the ion, but I'm not sure that's a word. I think you know what I mean. So they're not inactivated down here. Ooh, I'm supposed to draw an arrow. I don't want to make this too messy. It's going to get pretty messy pretty quickly. So at that stage, they're what we call inactivated, activatable, and they're closed. So there is a gate inside the sodium channels. All right. So the pore is closed. And that's the voltage-sensitive gate, the voltage-operated gate. But the inactivation gate is open. So often you'll see a picture of the sodium channel, and this is just formal, all right, where there are two gates, all right, and this would be the case where this is the sensitive gate here. So we're going to say voltage-sensitive, and this is the inactivation. So it's open. Now, they're not arranged like this, by the way. But this is open and this other one's closed. So the fundamental thing is you just have to close one of them, or both of them, and the ions will not flow. But both have to be open for ions to flow. So that means that on this upward stretch, this voltage-sensitive gate is open, but that inactivation gate is closed. All right? So way up here, that one gate is open, okay, but the inactivation gate then closes. So that's happening right around here somewhere. And you see that? That's not too horrible a mess. So that's, we'll just write it here, inactivation. It's inacting. All right. But before that happens, okay, it's open on the way up, right? So they're both open. So ions are able to flow. So that's what's happening all along here, right? Gates are open. Now I'm going to tell you, if you don't have an activation, and this is supposed to line up here, and the voltage gets to the equilibrium potential for sodium. So both gates are open just before an activation. Again, this is just for thinking about this. Will ions be flowing or not? What's the overarching rule of net ion flow or current at the equilibrium potential for a given ion, in this case sodium? Zero. So as the voltage starts to go up to the equilibrium potential for sodium, the channel can be wide open, and this is measured, you can do this, and the current will stop. because it's got to that voltage for the equilibrium potential for sodium. And remember that voltage, that counteracts the ion gradient, right? Just get outward voltage, inwards, I can't do it, inward sodium, so you can draw equal vectors, all right? But so what that means is in the end, we only have sodium and potassium and they're driving the exponential. The exponential processes, in essence, between the equilibrium potential for potassium and the equilibrium potential for sodium. And under normal conditions, that's all it can do. Can't go any lower, can't go any higher. You need other ions to make that happen. But if you have sodium and potassium, this is where the exponential goes. It defines the exponential, right? It's another way to think about that. So now, we have the last piece in terms of how current will flow. Right? So we said at the equilibrium potential for that ion, okay, there's no net flow. So down here at this undershoot, an overshoot, we have an undershoot. Said that has that potassium, so sodium channels then, as you reach the top of the exponential, they do inactivate. And that's why it takes such a sharp turn back down. Because remember, there's a little lag, and then this big potassium conductance comes in. And potassium, of course, drives the membrane potential all the way back down, through zero, all the way back down to the equilibrium potential for potassium. But at that point, potassium stops flowing. It's the same deal. Those channels are open, okay. Lines did flow, and since they still stay open, it really just clamps it down there, okay. So, at this stage, when let's start going a little bit backwards here, but I think it's more instructive. If we are, say, right here, at this point, that's a long way. So now sodium channels are gone. Now we're talking about these potassium channels that are real strong. Okay, so they're open and they're dominating. But you're at that little that position. You don't see a little squiggle there, right? Question mark. Okay, you're a long way away from the equilibrium potential potassium. So we said at the equilibrium potential, there's zero net ion flow, but you're well away from it. Okay, what's going to happen? Really strong current, right? So if you're at that particular voltage relative to the equilibrium potential for potassium, and it's a long way away, what do we say? That is a strong, do you remember that term we had? As you get more and more away from the equilibrium potential, you're at that position. So for that channel, for that potassium channel, I already said there's a lot of current flowing. What do we say operationally is happening? Remember that was the last term on that list that we talked about yesterday from the very front of the lecture, remember? So somehow you're way away from the equilibrium potential. The gradient, so what's happening at this point? Let's go ahead and add the potassium channel here. And now it's wide open. So now we have potassium, and it's going out like gangbusters, right? Really trying to make the outside more positive relative to the inside. That's why it brings it back down to that equilibrium potential, which is a negative number. Okay. So it's bringing it down, it's pushing it down, think of it as driving it down. So we have a really strong driving force. Actually, I've never done charades in the lecture. Maybe we can do the whole thing by charade. Okay, so at this point, okay, we can notch it over here. There is a very strong driving force, okay? And so, I'll draw it over here as well. So this is a very strong driving force. And so as it goes down, the driving force gets less and less. And I've run out of room because we're getting to zero. So if we were to look at this, you would say that when you're away from the equilibrium potential for potassium, okay, and you're way the heck up here, very strong driving force. But as the voltage comes back down, the driving force gets less and less and then goes to zero. We can draw the same thing for sodium. Okay? So at resting potential or equilibrium potential, take your pick, is the driving force for sodium very, very strong or is it not so strong? It's very, very strong. The system is geared so that as soon as it starts to respond, so even if you're at threshold, you're still a long way away from the top, right? So let's say you're here, all right? So you still have a really strong driving force at this point for sodium, a very strong one. That's why it really pushes it right up. Okay? So that's the last piece of the puzzle in terms of just describing the basic parameters, the basic driving elements to how this works, right? So you can draw a bunch of arrows in the reverse direction for sodium. So very big at the bottom, and as you get higher and higher and higher up toward the equilibrium potential for sodium, then it goes to zero. And that's why even though the channels are inactivated, okay, I mean, they're still open, all right, and not inactivated, all right, the ions are still not flowing. Okay. So I know it's a little bit of a mess, but we can come down here. The question is, and this could be hard to line up, I'm going to have to draw some of the cheat codes. Okay. So let's look at the currents, and I'm not going to necessarily give you a, oh, actually what we'll do is we'll do out over in. Okay. So this even though this is charging, we're going to say this is still pretty rapid. So I'm going to make it kind of a little squiggle bit here. So now we're talking about just the overall current. Okay. So at this stage, now you're starting the axe potential motor right under the axe potential. Okay. Where is the overall current going? Particularly as you get and go above threshold. Okay. Well, we already said sodium is going in, right? Potassium is going out. Remember what happens to that current? It goes, so it goes in, goes in, goes in. All right. But now, this is supposed to be, okay, this is supposed to be lining up with the top of the axe potential right there. Okay. Can you also, I'm going to move this up. You can see enough of that at the top, you got the idea. So this is now, if you look at the current, remember charge flowing, this is now reinforcing what we just said. All right. What's happening, the sodium's coming in, it's really dominating now on the way up, okay, but it's getting closer and closer to its equilibrium potential for sodium. So the current's really strong, and then it gets weaker and weaker, doesn't it? So that by the time you're getting close to the top of the axe potential, it should be, if not close to, but if you're right at the equilibrium potential for sodium, stop. So we can measure that. Use that voltage clamp that Hodgkin Huxley put together, right? That they basically created and defined. Okay, so now you're measuring currents. That's the I. I didn't write which I in here. Okay, that's okay. But as we know, that's dominated by sodium. It's going in, inward directed. So again, put the pieces together. Gradient's going in. Sodium is causing the rise to the axe potential. As it's flowing in, that's current. So we get this current, we get this transient current. But as it's getting up here to the equilibrium potential for sodium, that's why it slows down. Okay. And then right around that perfect timing. Okay, again, the system's unbelievable. Right around there, then the channels start to inactivate, and by the time you turn the corner on the either at or near the top of the overshoot, then they all inactivate. And they activate quite quickly. Okay. And then what happens? Potassium is going out. So how are we going to draw that? Well, now we have potassium going out, big time, and it goes and goes and goes to the point where it should stop. Right. Now, in the voltage clamp experiments, you saw this. You didn't see the whole bit as you would have in an axe potential where it should come down to zero. Why? Because once you're down to the equilibrium potential of potassium, that will stop too, right? They did it under conditions where that didn't happen. Okay, so it goes in, and then it goes out. All right? Now, I haven't drawn this perfectly. In fact, it should probably look more like this. That will depend on what's happening down here. But at this point, when you've really gotten down to the equilibrium potential of potassium, the current should stop. So this should be, I was going to write 0 there, but it was going to bulk out, but out. And then we'll take this over here. So that's the 0 current. Okay. Currents we measure in amps, usually in this case in nanoamps. All right. So if you look at this waveform here, okay, as it's coming back down to the undershoot, this is actually basically, for those of you highly mathematically inclined, this is basically the first derivative of the exponential, right? So these two key things you want to try to be able to draw yourself or recognize, okay? We've seen them in pieces, but now what we've done is we've lined up the current to some degree, not perfectly, right below the exponential. One of the figures in the PowerPoint has that. And then we can also write one more thing down here, G. What is G? Where did it come from? So again, this is part of the details. So remember, the relationship in this electrochemical cell follows basic electricity. And basic electricity and flow of current follows Ohm's law. What is R? Resistance, right? Voltage, current, resistance. So it's the voltage is a product of the current and the resistance. But remember, when you have an ion channel, it is basically a resistor, but we think of it conducting ions. Therefore, we really think about this from the opposite view, right? If it conducts, it has conductance, a relative amount of conductance. So remember, the conductance is, I should have drawn this differently. It's a reciprocal of, the conductance is a reciprocal of the resistance and vice versa, all right? So these are the three pieces, right? So the relative conductance, how well the ions flow, you can model that as a variable resistance. So less resistance, more ions flowing, more what? More voltage. Okay, for that particular ion. So very simply down here, we're going to say that because we know this is now basically sodium and potassium, this isn't perfect, but that's okay. You know that the conductance for sodium, now I'm going to make a mess, but this is okay. We know that it goes up and goes down pretty quickly, right? Conductance we put in the same direction. All right, either goes up or goes back down to nothing. Okay. So the key thing is that change in conductance for potassium happens with a lag. Okay, it comes up. Okay, we're going to make it look different. Put a little bit of a bunch of, I'm going to make a mess here too. So and remember, it's really big too. These are supposed to be big. So the key thing you have in mind is that the potassium channels respond, but they've got a time delay, right? They respond, but they have a time delay. Sodium channels respond right away. They're trigger happy. They're ready to open. Potassium channels, again, the ones that are responsible for the downward movement of the voltage at the back end of the exponential, okay, they're a little sluggish. But that's how the system is built, right? It's built to be sluggish, so they really open after sodium channels have done their work. They're opening a little bit ahead of time. Okay, they're starting to go, but they have that built-in delay. And you can see why evolution has made the perfect machine, right? Because it's all about, life is all about timing. So sodium does its work here, potassium then, and then it just stops. It just says, okay, I'm done. Potassium channels come in. So that's why we talk about this orchestrated ionic conductance change, sodium first with inactivation, and then potassium channels. Now the potassium channels also inactivate as well. Okay. Why? Well, when you get down here to the undershoot, okay, if they didn't inactivate, what would happen? Voltage would stay there, wouldn't it? So now they inactivate at this stage, and then the membrane potential comes back up to rest, because now that little resting potassium conductance takes over, as well as the leak. And remember, they're real small. So that's why the undershift takes a long time. Now down there as well, the key thing that happens here is that that sodium channel inactivation gets released. But the sodium channels are closed, because at that voltage they're closed, at the higher voltages they're open. So all these features are all dependent on where the voltage is. Okay? So you might see this in the text, might be a little confusing, but think of it more operationally like this picture here. So we say that sodium channel inactivation here is very low, if non-existent. It's low down here, the sodium channel inactivation. But the channels are closed because that other gate is closed. The voltage sensitive gate is closed. It closes down here. So the voltage sensitive gate down here is closed, but the inactivation gate is open. So we say inactivation is low or 0. And then as we get up to here, we know that voltage, the sodium channel inactivation is high. So now we get back down to here. That's the state. We call it state dependent. When the voltage gets back down to here, sodium channels sense that, and they swing open the inactivation gate. Okay? But they're closed, because at this position, this is very strong for keeping the voltage sensitive gate closed. And something similar happens with potassium. But we'll just for purposes of discussion, because it really counts, talk about just the sodium channels. Okay, was that clear? So in terms of that voltage sensitive gate, it's really, really sensitive to the voltage changing toward more positive direction. Okay? So it opens, right? And it opens so fast that that inactivation also has a little lag to it. Okay, so they're real trigger happy, like to open. They open up here, okay? And then that inactivation gate, where inactivation is very strong, then swings this other gate closed up here, and for a second, well, for a moment, not a second, a microsecond or two, that voltage sensitive gate there is still remaining open. Okay, so it's inactivated, and as it turns back this way, then, okay, as you're moving back in this direction, then the voltage sensitive gate starts to close. And it closes fully down here, and activation gate swings open. So that means that those channels are ready to go, right? Potassium channels also have to get ready to go. So the ones that are responding here that give that real strong potassium current to bring down the active potential, they got to reset as well. They have to reset. Okay. Kind of cramping our side, but that's okay. We spill over into the next lecture in terms of ion channels. So, questions? The other way to approach this, and I recommend doing this, is to draw these things with nothing on it. And just try to remember what you can put in. All right? Where are the equilibrium potentials? Where should the threshold be? Okay. What about the sodium channel inactivation? Where does that happen? Just do it step by step, because you know what that you can all draw this. And I think you can all draw this. It's pretty clear. Sodium, and if you go ahead and write on there, sodium's going in, well, the current must be going in. And potassium's going out, well, then the current must be going out. All right? And then a little more complicated bit, which is that, well, if sodium's going in, there must be a strong conductance for it, right? Which normally be high conductance, low resistance pathway. That's where the conductance happens. And then there's this lag with potassium, so we get the second up. Okay? So do you feel better about the active potential now? Or now you're thinking, oh man, I could draw that squiggle, but what is all this stuff it's making me know? This is the heart and soul of neurobiology, right? Okay. So I'm trying to help you do is to think about it step by step. You can get a little tricky where the ion gradients, where the equilibrium potentials, You know, there's this bit about this driving force. Add the driving force concept in later. Okay. Think about the ions flowing, the currents. Okay. Add in that inactivation, and then start thinking about some of these other properties. All right. This is not the last time we're going over this, because we'll have the class review. Okay, shift gears. I'm not going to rocket through this, so we'll see how far we go. This is actually a very short lecture. Oh, the other thing is, this was a lot. We had the challenge questions. We're going to save them for later, so we'll just chew on this a bit, digest. Hopefully you won't regurgitate all of it. So then, you know, you'll really have that in mind. And go ahead and look at the challenge questions. Have any of you done that? Probably not, right? We brought out something which we alluded to very early on. You know, can an action potential go the opposite direction? What happens if we had no sodium channel activation? What would that action potential look like? Things like that. Okay. So get all those concepts in mind about propagation, about the ion channels that are working first, and we'll come back to that. Okay. Yes. Trying not to run up to the last minute every day, but we do have a lot. So let's talk about ion channels and perspective of excitability. And so some of this is kind of fun for those who like to see little things moving, because I have a couple of movies. All right. So the main thing we're talking about today, though, is what ion channels, what they look like, how they operate, what we call their structure versus their function. Structure dictates function. So a particular arrangement of the protein in the membrane, or proteins, because in some cases there are subunits, in some cases there are domains, but one way or another they make this big, funky-looking thing with a hole in the middle of it, right? And we know that that's the ion core. Okay? There were some amazing surprises when the actual structure of the channel was determined. And this was determined first, the potassium channel. I don't know if you can see that down there. It was done by Rod McKinnon at Rockefeller University. Some of you may have not heard of Rockefeller University. You think that might be a joke, but it's actually one of the premier universities in the world. It's just they don't have a football team, and they never will. They have no undergraduates, a very small graduate program, and it's all research. So he took on the challenge of trying to determine the structure of a membrane protein, not just an ion channel. And until he did this, nobody thought it could be done. So you can't crystallize proteins out of a membrane. Okay? You just can't do it. And he came up with some extraordinary tricks to do this. He mutated it, put it in a lipid environment, got crystals, was able. So use something called X-ray crystallography through diffraction allows you to get back, it's a path back to find out where all the atoms are, and you get the structure. Okay? So he solved it, and it really was monumental. He did it in the late 90s and received the Nobel Prize very shortly after for that. So just with the action potentials, you have a list of features that are important to know about ion channels. And so we see some distinctions. So with sodium and potassium channels, they actually are formed from one big single protein. So what I showed you before, the potassium channel, that's actually 4 bits. So if you think about the channels, you're going to think about 4 to start. So with the sodium and calcium channels, they have 4 domains. Okay, so they have these sort of bits, okay, that wrap around, if you will, to make the pore. Potassium channels has divided it up, so they have 4 subunits replicating the 4 domains, but they're separate genes, okay, and they make, so they're really in the same vein, they make 4 elements that surround the center gap or cavity, and that makes the pore. So all the voltage gated channels have voltage sensors. Alluded to that in the very first lecture. Okay, so there's a piece of the channel out there that senses the voltage change, and it moves. And when it moves, that opens the channel. Excuse me. Usually on the outside, almost always on the outside. So that opens the ion pore when the voltage sensors move. The ions move across the cavity through the pore, all right, and it turns out that all the ions in solution are hydrated. We don't really go into this a lot of detail. But so the ions sitting there are actually surrounded with a particular number of, they're not really coordinate, they're hydration spheres for each ion. So when ions are going through solution, they're not going by themselves. Okay. So your old pictures you've looked at in a textbook on chemistry with sodium and potassium floating around. Well, they are, but they actually have water, ordered water all around them. And that won't go through a normal voltage-gated ion channel. Okay. So the hydration sphere is actually stripped off, and then it goes through the narrowest part, which selects which ion. Okay. And the amazing thing that McKinnon discovered was that that pore, the arrangement of the amino acids there and their charges, they're absolutely mimicking the hydration sphere. So that exquisitely defines which ions can go through. So you might even have an ion that's a little smaller. You think, okay, it should. So if you had something that could go through that's smaller, why doesn't it? Well, it's because it's not interacting with the pore, which is mimicking the hydration sphere for that specific ion, and it won't flow. So this bit down here, it sounds a little complicated. You see it, we'll see it picture-wise, but this was the fundamental insight. And this was just from a guy saying, well, I want to see what the channel looks like. And spend 10 years just figuring out a way to say, what does it look like? We really don't know. Up to that stage, bare outlines. We knew something about the arrangement of the subunits. We knew there's a cavity in the middle, and people draw nice pictures, but nobody knew what it looked like. When we figured it out, we said, oh my God, it's perfect. The thing, though, there was a physiologist who had predicted this beautifully. And when he predicted it, in fact, the arrangement, drew a cartoon with the arrangement of these interacting elements. It matched perfectly with the structure, and McKinnon was floored that this individual had figured that out. So the other little thing, this is a little bit more of a sidebar, this is more physiology, but it helps you to think a little bit about these ion channels. They usually, not always, but many of them can conduct ions in opposite directions. It just depends on the driving force, okay? So if we did something a little crazy, all right, we took the axon, and let's just say we eliminated the sodium channels completely. We just want to look at potassium. You remember how you can eliminate the sodium channels? Remember the name of that toxin we can add? Tetrodotoxin, or TTX. We put that on, sodium channels are not going to work. Just look at potassium, okay? But let's do something crazy. And let's say the equilibrium potential of potassium is around about minus 80, which it is, minus 75, minus 80. Let's put the voltage at minus 100. What's going to happen? Number one, you're away from the equilibrium potential. There is a driving force. The driving force is going the other way, though, isn't it? Potassium wants normally going out. It's going to drive it in. All right. So you look at that. Ions will flow. So artificially, you say you want to ask the question. You put it. I'm just going to tell you. Put the membrane voltage at minus 100. Okay. Potassium will start flowing in through that channel. So that operationally shows you that the potassium can go in either direction. All right. Now, normally you're never down there, except for extraordinary circumstances. So really, the reason why the ions go in the direction they go is because of the gradient and where the voltage is. Okay. And the inactivation gates are separate elements. So we'll go through this pretty quickly. So this is again a picture of a particular type of potassium channel. So this is, there's different subunits. I don't want you to pay much attention to this. This is much more informative. This is looking downward. So what do we say about the potassium channels? There are 4 subunits. I don't know how well that, can you see that well enough? That's why there are 4 colors. Okay, 4 subunits. But there's these paddles out here, all right? First saw this stuff, whoa, what are those paddles? Went back and determined the structure. We already knew where the voltage sensors were from mutational analysis. We knew where they were in the sequence, didn't know how they looked in the structure. They're sticking on the outside. So pore on the inside, you have these voltage centers on the periphery, okay? So we know then that when the pore is closed, this is not showing the gating correctly, but we do know that there is a major conformational change, okay? So it was fairly clear very early on, just looking at the sequence, that that voltage sensor being on the sort of the outside away from the pore, when it moves, and it moves in the plane of the membrane, okay, it's basically tugging on the elements around the pore to open up the gate. Okay, and here's a better picture of that. Okay. And we know that so this is, you're not able to see it so well. We're going to see this animated in a second, but this is showing a very large, so actually the voltage sensor here is this S4. So you see it moves a lot, and it tugs on this system enough, and it causes a really big conformational change to open that pore. Okay, here it's showing in sequence again that gate. So it's this little bit here. It's going up, 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 up like that. So let's look at it in action. So this is just sort of a cross section, just looking at one of the voltage sensors here. Okay, and you can see that. So look at the green with the blue, the light green with the blue balls on it. All right, that's the voltage sensor. There's other bits here. They anchor. They have other interactions. Turns out that the channels actually interact with the proteins too to stabilize them in the membrane, localize them. But that's the paddle out there. That's the sensor. So see it move and look at how it's causing it by moving. And this is in the plane of the membrane here, and it's causing a very, very dramatic change in terms of the conductance, the structure. So it's flipping. It's basically rotating and opening up. And we can see that even better now. So this is the side. Here's looking down. So there's the sensor. In this case, we're going to see that it not only moves up, it moves laterally. Okay, and look what it does. And now we're actually looking at the bottom of the channel. Okay. You can see it enormous. It's not showing the whole thing, but this is around. So the gate is actually made up from each of the subunits or each domain. Okay, and they rotate and open up, kind of like a diaphragm. Well, I think it's cool. And we know that the sodium channels and potassium channels operate in a similar way. But again, sodium channels, one protein with 4 domains, so they come around and create the same basic pore structure, but with a different selectivity gate, so that only sodium goes through. Okay, sodium is smaller than potassium. Potassium, it takes 4 of the sodiums, they come together. Again, we said sodium doesn't go through the potassium channel, okay, even though sodium is smaller than potassium. And that comes to this picture here. So this is looking at a cross-section showing ions flowing, and this was actually derived from structures McKinnon did where he was able to trap the ions in different positions going through the pore. But that also was quite a trick of science. So again, they're hydrated, not showing them that. So what happens is they're going down through here, and then the ions are interacting with these elements which are mimicking the hydration sphere. And the thing that was real weird was that right in the middle of the channel, there was this vestibule, and the ions got rehydrated right there. So as soon as they get through the selectivity filter, even though they're in the plane of the membrane, there was this weird thing where there's this vestibule. So there's selectivity, the vestibule, and then the gate. Okay. And you saw it for both potassium and sodium. And it's still not completely clear why. Now, why not just let the ions plop out the other end? They can rehydrate. But there may be something in terms of basic energetics that I don't know. In fact, there's probably something out there about how when you dehydrate the ion, you can only do that for a moment because the ion flux is really, really fast. I mean, they're just zipping through. So the idea is that they dehydrate very, 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 basically as they interact with the selectivity filter, that first strips off the water, it goes bing, bing, bing through, and then the water comes back on. Because I think the ions and actually the energetics of it are such that it's not a good thing to have the water off of the ions. So it has to happen very quickly. And then now we're getting down toward the last bit of this, which is the inactivation gate. So the activation gate, first discovered with potassium channel, ends up being basically this long extension of structure of peptide, really, off the protein that has a globular end to it. And it is sensitive to voltage, right? Because remember we said it depends on the position of the sodium channel. It's easier. Remember, low inactivation around the resting potential, real high inactivation. So this thing senses that voltage, and it turns out it swings around and basically plugs the pore with this structure. So it's not a gate that goes like this. It's actually like a drain in the tub, right? It swings around and plugs the hole. Okay. So this is one of those crazy things in science. Nobody predicted this. before, it was demonstrated where that inactivation gate was before we saw the structure. It could show that if you remove that inactivation gate, you could actually just clip it off with a little enzyme, a protease. So you knew there was just this little nubbin, but had no idea that it was this swinging thing that just came around and plugged the hole. So it's called a ball and chain mechanism for channel inactivation. We're almost done. Now this is a little complicated. This is just showing, I don't want you to be able to draw this or even memorize it. This is just showing, though, that if you look at the current, okay, so this is outward current, inward current, in this case for sodium, you can actually plot the movement this way and show that, in this case, even with the sodium channel, if you go to the right voltage, okay, it will actually go out as well. Where is that going to be? Way, way above the equilibrium potential for sodium. So now, again, artificially, you put the membrane at plus 100 millivolts, way up there. Sodium will go out. So again, this is just a formalization of the idea that the ions can move in either direction. Well, it depends on the driving force, but the normal driving force, where does that run for an action potential? And where can it only run? Between the equilibrium potential of potassium and the equilibrium potential for sodium. So we're really only talking about sodium going in or potassium going out. Oh, the only other thing to point out is, okay, that's true. So in the basic ion channels that operate the action potential, ions can go in either direction. But it turns out there's some tricky ion channels out there that only let the ions go in one direction. They're called rectifying because they rectify the voltage. So some of them are a little tricky that way. You run across that. But fundamentally, with the sodium channels that we know for the action potential, and potassium channels we know for the action potential, ions can go in either direction. And there's your features again. Okay. Questions? Well, think on it a bit, and we'll pick it up on Tuesday.